Hello, this is Andrew O'Brien, Mac May, and Adam Johnson, and we're doing our project on equivalence proofs in the Coq programming language. The motivation for this topic in equivalence proofs that we're doing is a more advanced form of behavioral equivalence than we've seen before. Previously, for programs without variables, correctness through equivalence was pretty easy to show. All a program needed to do to show a transformation was correct was if two numbers evaluated to be the same number. For a full IMP programming language, though, you have to take into account variables and states as well, so that sort of simple transformation won't work. Consider AEXP and BEXP. A new form of behavioral equivalence for them is this idea that two AEXPs and BEXPs are behaviorally equivalent if they evaluate to the same result in every possible state, which is formally stated in the slide. There's also the notion of command equivalence. Two commands are behaviorally equivalent if they evaluate to the same ending state whenever they are started in the same initial state. Behavioral equivalences have some interesting properties. For one thing, they meet the formal rigorous definition of all equivalences in that they're symmetric, reflexive, and transitive. Finally, behavioral equivalences are congruent. If two subprograms are equivalent, then their parent programs are also equivalent.
Program transformations. A program transformation is a function that modifies a program, taking one program as an input and outputting a variant. Constant folding is one example. The property of soundness means that a transformation preserves the behavior of the original program. The constant folding transformation. Constant refers to an expression that lacks variable references. Essentially, this means that they are reducible by default to simple values. Constant folding optimizes programs by replacing constant functions with values, so that it need not be calculated each time when run. Constant expressions apply to any variable, from numbers to booleans. Constants in a command can also be folded by applying this function on all embedded expressions. Soundness of constant folding. Of course, it must be proven that constant folding is sound. For both numbers and booleans, it must be shown that for all expressions x is equivalent to the fold constant function applied to x. Proving inequivalence. A program and its own variant via something like constant folding are equivalent, as we have proven. We focus now on similar cases which are not automatically equivalent. The text asked us to provide an example of an expression fitting this reference which isn't equivalent. My example is if x equals x plus 1. In such a case, an attempt at replacing instances of x in y with the expression equivalent to x would produce a non-terminating recursive loop. This would be because the expression lacks soundness. It cannot be simply reduced to a primitive value, and thus is not a candidate for constant folding. Here is the function that produces the result described above. Here, we see the definition of the substitution equivalence property, which does not hold for all x1, x2, a1, and a2. In this case, the example I came up with is the same one provided in the text, though their reason for a lack of equivalence is slightly modified. While they do not, apparently, recursively substitute each new x with the full x program, The fact remains that as x is, itself, a variable, folding in this manner causes the successor function to run twice rather than once, which is trivially unequivalent. As long as we exclude cases like this, specifically cases where the variable x appears itself within the first x function, the equivalence is proven true in all cases.
So now we look at some actual Coq code coming from the Programming Foundations chapter on program equivalence. So in the slide test for true, the authors are drawing attention to the fact that you wouldn't actually use a guard whose conditional is literally true, but rather you choose a guard that is equivalent to true. So the theorem is used that if B is equivalent to Boolean true, then a test of B results in C1 via then, else it results in C2, and that it's a given that it's equivalent to C1 because B is provided as Boolean true. So we have to show via proof in the Coq code that ST and ST prime, that if ST is equal to test of B, then C1, else C2, that yields ST prime. And then ST is equal to C1 yields ST prime. So basically we're just adding the additional ST prime to show that going from ST to C1 via B, given that B is Boolean true, yielding ST, that then it's a given that we get ST prime. So we need to proceed by cases on the rule, and these two cases are E if true and E if false. And it's fairly simple to see that E if true is the case that we want to use here. Given the premise that E if true, ST C1 ST prime was the example that we gave. If we used E if false, then we know that the evaluation via B eval of B would yield false. Thus, the evaluation of B would not go to C1, but rather to C2. So we'd have a completely different rule, that ST would go to C2 to ST prime. So given that B is equivalent to Boolean true for all statements containing B, that would be a contradiction when using E if false. So we can see in the proof provided in the Coq code that by applying E if true, we use that assumption, and then we unfold to the BE equivalence, and then we rewrite the HB with the reflexivity rule, thus yielding a proof for the fact that B equivalence B is equal to B true, thus that B is equal to Boolean true. Now we move on to the slide showing program equivalence in IMP. Here the authors provide a series of small programs in Coq's imperative language, programs A through I, and ask us to show which of them are equivalent. So showing that program A is equivalent to program D, we look at A to see that the test is while x is not greater than equal to 0, then x is equal to x plus 1. In program D, we have a bit of a modification. We've got while x is simply equal to 0, so there's no test for greater or less than, is not, equal to 0, then x becomes x plus y plus 1. So we've also got that addition of plus y. But the equivalence is shown through the fact that the test is for x not being equal to 0, and in each case of that, x being incremented by 1, which is true in both programs A and D. Moving on to program B, we see that it is equivalent to program E. So B is a test of x being 0. If that's the case, x is incremented by 1, y is set to 1. And if it's not the case that x is equal to 0, then y is set to 0. And finally, x is set to be x minus y, and y is set to be 0. So we're getting 0 in either case for y, and we can see that in program E, y simply is set to 0. So even though x is a separate part of program B, and there are tests there, if then else statements, program E and program Y are equivalent in the fact, program E and program B are equivalent in the fact that they both yield a y of 0 in any case. Program C is programmatically equivalent to program H. We see that program C simply says skip. H is a test of x not being equal to x, and then x being incremented by 1. So we sort of have an endless loop here where x would just be incremented by 1 each time, and we want to see that x is not equal to x. So this gets skipped over because it's a test for x not being equal to x. Finally, we see that programs F and G are functionally similar. In program F, what we have is y being set to x plus 1, and then the test is for x not being equal to y. We set y equal to x plus 1. So we have inequality between x plus y, between x and y, rather. So it's always going to be true that x is unequal to y, and it's just going to loop endlessly. In program G, we have simply while true. So this is literal true. This program isn't taking that step of creating an actual command that's equivalent to true, but rather stating just true explicitly, do skip. And we can see that that's equivalent to what we have in the while section of program F, because x is never going to be equal to y, so it's always going to be skipped there. And then program I does not have any equivalent program to it. In the slide on congruence, we have a simple example of two programs that are shown to be congruent. So the theorem that the authors provide, the CSEQ congruence, shows that for all C1, C1 prime, C2, and C2 prime, that if the command's equivalence is shown between C1 and C1 prime, that this implies equivalence between C2 and C2 prime, and then that we can show equivalence between C1 and C2, and C1 prime and C2 prime. So we see just two very simple programs here in their congruence example. We've got x is equal to 0, test of x being equal to 0, then we've got y of 0, else y is equal to 42. So very simply, because x is 0, we're going to get y is equal to 0. And then we've got a congruent program in program 2 where x is set to 0, we test if x is equal to 0, and then we get y is equal to x minus x, else y is equal to 42. So once again, we see that x is going to be set to 0, thus the first clause is going to be returned, not the else clause. In the first one, y is explicitly set to 0, and then in the second program, y is set to x minus x, but because x is initialized to 0, x minus x simply is 0. So the proof of this is actually a bit more complicated. We apply that CSEQ congruence between C1 prime and C1 and C2 prime and C2, showing that the inputs match to the outputs in the same way between the two programs, and thus that they are congruent. Finally, the Programming Foundation authors show inequivalence via Coq code. In the Proving Inequivalence Part 1 slide, we're supposing that C1 is a command with the form x is equal to A1, y is equal to A2, and C2 is a command that's going to be compared to that, where x is equal to A1 and y is equal to A2 prime. So the difference between commands 1 and 2 is in the y. In the first, in C1, it's equal to A2. In the second, in C2, y is equal to A2 prime. And A2 prime is introduced as being formed by the substitution of A1 for all occurrences of x in A2. So making that clear, C1 could be x is equal to 42 plus 53, and y is equal to y plus x. In C2, because the x's are A1 for both C1 and C2, x is once again 42 plus 53, but y, because it differs between A2 and A2 prime, it's y plus 42 plus 53. So rather than simply being the y plus x that was shown in C1, it's y plus the literal x from C1, which is 42 plus 53. So we see this shown in the COC code for the SUBST AEXP substitution AEXP, where we have A. So we show addition, so A plus, A1, A2, that yields X, U, and A1, and then X, U, and A2. And we have similar setup for A minus and A multiplication. So in the example, we have the SUBST AEXP X of 42 plus 53, and then y plus x, and we show that it is equivalent to y plus 42 plus 53. We have definitions below that showing that there's an equivalence of x1 being a1, x2 being a2. Once again, x1 being a1, as we saw, there is no a1 prime between command 1 and command 2, and then x2, we see that that's the substitution AEXP x1, a1, a2. So that's not just returning a2, but rather the a1 of x1. So in this case, there is not an inequivalence, but there is the possibility for an inequivalence that was not revealed here that will be shown in the next slide. So in the final slide on proving inequivalence, we use a similar setup to show that commands C1 and C2 are actually not equivalent, despite our attempts to make them so, or to prove them so. So we're using remember to show that x is equal to x plus 1 and y is equal to x in command 1, and x is equal to x plus 1 and y is equal to x plus 1 in command 2. So the difference there being in the y in command 1, y is equal to x, in command 2, y is equal to x plus 1. Below these remembers, we have the assertion of command equivalence between C1 and C2 via substitution, and this is what we're going to show to be not true. So we have further remembers where y is mapped to 1, x is mapped to 1 as well in statement 1, and then in statement 2 we have remember y is mapped to 2, x is mapped to 1. Finally, we have assertions where we're trying to show that command 1 produces state 1 and that command 2 produces state 2, and we want to prove this via substitution. So by the definition of the command equivalence, we have x is equal to x plus 1, y is equal to x plus 1 produces statement 1, and then we have the same, x is equal to x plus 1, y is equal to x plus 1 yields statement 2. So statement 2, where y yields 2 and x yields 1, we're attempting to show that that's equivalent to statement 1, where y yields 1 and x yields 1. But that's not true because we have y yields 2 in statement 2, which is where these two diverge. So simply by asserting equivalence between them, where we have x's and y's in two commands, because they diverge, when we do the test for equivalence via the substitution attempt, it will be shown that they are not in fact equivalent.